So now that we've learned all the different variables of the weather and how they influence each other, we're going to take a look at the overall planetary scale of the atmosphere. Uh, we're not looking at little tiny thunderstorms or even a front. We're going to look at a global. If you averaged everything out over a number of years, this is how the atmospheric weather would look. So it gives you a good idea of a starting point of what you could expect anywhere in the globe. So with that, let's move on to, supposedly you had a non-rotating Earth. We don't. So one side would always be dark, one side would always be sunlit. Oh yeah, the most intense sun would still be at the equator coming in. So you would get the most heating there. We know heat, warm air rises. So basically what you would be doing would be creating a circulation that one side of the planet would have the air lifting up, the other side of the planet would have the air sinking. Well, we don't have exactly that. We have a rotating Earth, so that's moving. But by the same token, we know that the coldest air is over the poles, and the warmest air is over the equator. So we're just moving this around the globe. So that is a basic circulation we have. With the rotation, it adds some complications, naturally. So you wind up with belts of winds. So they're basically 30 degrees each belt. So around the North Pole, we have a belt of winds blowing around the North Pole or the South Pole. Notice, winds converge towards the equator. So that's where the intertropical convergence zone is. And along that band is thunderstorms. Notice around 30 degrees north, they diverge, which means there's probably some kind of clear air there and high pressure. Oh yeah, if winds are coming together, the winds are probably creating a pressure gradient, so the surface is probably, winds are probably a little stronger where they're coming together. 60 degrees north, they come together. When they come together at 60 degrees north, we got lots of lows up at that latitude. So that is the general pressure pattern. And you can see just what I was talking about. And if you were to look at a globe, analyze the pressure. Typically in January, we have strong low pressure, Alaska, like Greenland, into the northern part of Europe. That's the area of low pressure. We have very high pressure just a little further south along the other area. And then we go along the tropics and we have more low pressures. If you went into July, push everything to the north. So this big high pressure that was sitting out and a little weaker becomes stronger and more intense and moves further north, or Bermuda High. If you're along the east coast of the United States, you've heard people talk about the Bermuda High lots of times. All it is the normal high pressure system that we just looked at. It pulls in moisture on the western side of it. On the eastern side, it's pulling air down, sinking. That's why the east coast of the United States has a lot more precip during the summertime when this high is in effect than the west coast of the United States would. They have the same kind of high, but they're on the eastern side of that high. So the air is sinking, cooler air is coming down. And these semi-permanent circulations, you look at them, they influence the pressure at the surface in such a way that they actually cause currents in the oceans. Excuse me. So we're going to talk about that in a minute here. We'll talk about the polar vortex in a minute, which is just a very strong circular circulation that's across the poles all the time. Depending on how strong it is as to how much cold air is going to come out of this area and down towards our area. Let's take a quick peek here a minute. I wanted to show you something here. This is literally showing all these pressure patterns right now. If you looked over the Arctic, look at 60 degrees north, storm, storm, storm. 30 degrees or north, or a little lower now, and it's lots of high pressure, lots of less clouds. Oh yeah, where's the intertropical convergence zone now? Right here. Look at this line of clouds all along here and out into the Pacific, even if along the same line. So there's the intertropical convergence zone where it is now. It is moving north right now because the sun is coming north. So you can see these features literally looking at a satellite picture right now. So let's move on here. We had this polar vortex up to the north. The stronger the polar vortex is, the less cold air is going to come out. And in between that polar vortex, we have westerly winds that are just south of there moving along. So I might as well show you the next one I was going to show you. Here is a jet stream circulation that is occurring right now. This is at 300 millibars, good location for the jet in the wintertime, a little lower than the 200 millibar you might find in the summertime. So what I'm looking for here is high-speed jets of air, which are the color-coded here, and you have one coming into the western United States here, another one over the eastern United States here. Basically, you have a strong jet all around the globe right here. Notice the strong low pressure over the Arctic right now. Not as strong as it was earlier in the year. It was really intense earlier in the year. And that is why some of the Arctic air is making it south right now. So these are the jet streams. Think about it. On the jet stream, where the jet stream is, the temperature contrast is going to be the greatest. Well, that would mean I should be able to identify that there's going to be some kind of a cold front right along to the out ahead of this jet stream here. Well, if I can get this map to come up here, notice where the cold front is. Out ahead of that jet stream, this main cold front. And it is quite a cold front. I mean, temperatures will drop off into the 40s, and then even another cold front coming behind it with teens. Ahead of that, 70-degree air. So that is where the contrast is coming. And you can see that when you're developing these global circulations. So here we saw all these different wind patterns, different troughs and lows. And we can look at these here. Just looking at this slide, you can see tropical tropopause is much higher. It goes up and down in the mid-latitudes where we live, and then it goes back down to a lower, all because of these, and you have really three discrete areas you can pick out where the tropopause changes. Along the trade winds, which are the winds that are to the south, between that 30 degrees north high pressure systems. Remember, their winds are flowing clockwise around it, so that across the Atlantic, that's how people, when they had sailing ships, used to want to get to the U.S. They would want to take those sail and go across that way. And then here you can see the intertropical convergence zone, how it follows the sun. Notice it moves further north over land. Well, we've learned it takes a lot of energy to heat up water. The specific heat of water is pretty doggone high, much higher than land. So that is why over land, the hot air, the air is going to be heated more. The hottest location on the planet is going to be over the land, and it's going to adjust depending on this, where the sun is. So the intertropical convergence zone, that impacts things like monsoons. If the If the intertropical convergence zone has moved north of your area like it does in the summertime, then all of a sudden, for example, India is south of the intertropical convergence zone. Well, guess what's south of India? A whole bunch of warm water. All that warm water pulling moisture up into India, you get a wet monsoon. And the tropical convergence zone stays up there during much of the months in the summertime, so they're in the wet season. Now, in the wintertime, it moves south. Where do the winds come from? Out of Siberia. Siberia doesn't have any moisture as such. Very dry, cold. So they have a very warm, very cold winters and dry. Here you can look, I just talked about the two different sides of these highs over the ocean. Notice Charleston has lots of precip in the summertime. However, San Diego, nothing. Very dry. And here is the ocean currents. Notice the Gulf Stream. It's part of the North Atlantic Gyre and moving up along the east coast of the United States. Some of the Gulf Stream is fed from coming out of the Caribbean. Some of it's coming across the tropical Atlantic and up. It basically begins to pull offshore right about Cape Hatteras and move across towards England at that point. It's actually what helps to keep England a little bit warmer than it would be otherwise. We also have a monsoon in the United States, North American monsoon. What happens is there's actually a fairly high level topography out in this area. In the summertime, not much clouds at first, heats that high level, which heats the upper part of the atmosphere. So you wind up literally pulling in air from below, from the oceans, into that area, which rises. Oh yeah, we know that the hotter the air is, the slower the pressure is going to drop with height. We actually wind up with high pressure aloft, low pressure at the surface, but it is a semi-permanent feature in the summertime, pulling air in from the Gulf of Mexico and up into Arizona, New Mexico, maybe into Utah. When it's really going strong, you'll get lots of thunderstorms out there and lots of rain. This develops mainly in late June and July in that area. Rossby waves are long waves in the atmosphere. We can actually see it on the chart I was showing you. The reason I looked at the northern hemisphere is typically they're anywhere from 3 to 5 Rossby waves. There are lots of little short waves. We'll call these jet streaks a short wave. So we have a long wave that I would argue is right in here. Another one just off the west coast of the United States. Another one along or towards the east coast of the United States. One in here and one across Europe. It's a confused pattern. This is not a stable pattern. So it's going to be changing and shifting. But they're basically, anytime a short wave enters one of these areas, it's going to tend to want to intensify. When it's moving out of it, it's going to tend to weaken. So that's what Rossby waves kind of show. They kind of are general 3 to 5 waves across the mid-latitude you can see coming out from the poles. And they allow you to pick out areas. This is great if you're looking for 6 to 10 day or 8 to 14 day weather. It is a great way to anticipate what may be coming and how your weather may be evolving, whether you'll be below normal or above normal. So, moving on from that, with that, we also have zonal flows. Zonal flows are when everything is coming from west to east, very little ripple into the atmosphere. Yes, there's some, but not much. And then you get the meridional flow. Boy, we got one right now. We've had it for the last several weeks in the U.S. It's not moved much, and you know it's been fairly cold, much colder than normal in the eastern two-thirds, almost the whole United States. And that is because of the meridional flow. Think about it. It drops further south. It pulls in the colder air from up north. It also goes further north in the highs. So you create a greater and greater temperature contrast. Sometimes they get blocked, and we've had that too here lately. They're cut off. And here was a typical blocking pattern that occurred during the summer of 1993. Record rainfall in the Midwest, lots of flooding on the Mississippi. And here we talked about the jet streams. We've already talked about that and how the contrast in temperature is accentuated. The further up in the atmosphere you get, the closer you are to the tropopause, the bigger that jet stream contrast is. We know about how the wind streaks work now in the pressure gradients. Notice the jet stream goes further north in the summer, further south in the winter, all because it's following the sun. There are short waves rippling through these rod waves. I showed you those there. Where you have a short wave, you're going to have convergence versus divergence. Where you have the divergence aloft, we learned that allows the air below it to rise up. So along a jet streak, you're going to have divergence in the left front quadrant, in the right rear quadrant, convergence in the other one. So if you're in the left front quadrant of a jet streak, well, here you would argue that a jet streak would be moving right through here. This would be in the left front quadrant, right in here. What you wind up with is good divergence. This low is developing. Behind it, you have subsidence, sinking. You build the high pressure. Now, you've just related 3 dimensions of the atmosphere together. And you can see that in the jet streak there. El Nino and La Nina are part of global circulations as well. We have just transitioned from a La Nina pattern into a neutral pattern. What does that mean? That means for the first time in a few years, the temperatures across the Pacific are fairly normal. La Nina, they're colder than normal. El Nino, they're warmer than normal. The expectation is that El Nino is going to occur later on this summer into the fall. So temperatures will be warming in the Pacific with time. Along the ocean, there's something called the Ekman spiral. Ekman spiral is just, say I have a southwest wind along the Atlantic coast that is pushing the water north. Well, what happens is, just like any other northern hemisphere fluid, and we'll take the atmosphere as an example, we have the Coriolis effect. Well, what happens to the right? The water wants to turn to the right. Well, what happens is, as the water turns to the right, it keeps turning to the right with depth. And you wind up with a spiral called the Ekman spiral. It actually occurs in the atmosphere in the lower levels as well. We didn't discuss it. But with that, it can change the temperature along the coast tremendously. I have seen temperatures at Cape Hatteras go from 85 one day to 55 the next because of this Ekman spiral occurring. It also occurs right along the equator. El Nino can change the influence and how the weather occurs across the United States. Warm phase, you get lots of thunderstorms. You enhance the lift. You enhance the jets at the low levels, particularly easterly winds become stronger. This actually decreases the probability of tropical weather. La Nina, on the other hand, tends to be fairly strong further north jet streams. And with that further north jet streams, you'd think most of the cold air would stay up in Canada more typically. And this year actually did have most of the cold air in Canada till now. And now we are going into neutral, and now we're finally allowing the cold air to further south. There's a North Atlantic oscillation. Basically, you look for variations between the subtropical high that we've talked about and the polar low over Iceland. Depending on how that is, can really impact the eastern part of the United States. And here you can see that influence as well. And we have the Arctic oscillation. I looked at the circulation up there around the Arctic. The stronger it is, the less polar air is going to come out. So when the AO is very positive, you don't get a lot of Arctic outbreaks. When it begins to go less, go towards negative, you get more Arctic outbreaks. And that is what's occurring right now. So I think that's enough for this. Hope you got a little bit out of this. Let me know if you have any questions.